Will share my screen. Okay. So I'm actually giving this presentation with Laura and Tara. Tara's here, but Laura I think is running late from a meeting, but hopefully she'll be back by the time we get to her stuff in the presentation. But yeah, so as you can see, we're going to be working with an application called Max MSP. Totally fine if you don't have it yet on your computer. You don't necessarily need it for the meeting, but if you're someone that likes to follow along with workshops, I would go to this link and download it. So yeah. Okay, so welcome to the New Wit and New Sound presentation and workshop on ring modulation. So before we go into like all the technical stuff on ring modulation, we wanted to make sure that you guys actually knew what it sounded like. So, I need to make sure I share my sound. Oh, it is sharing. Okay, cool. So the most famous usage of ring modulation is probably in Doctor Who. The voice of the Daleks, if you've ever seen Doctor Who, and I think also the Cybermen, the Doctor Who uses ring modulation. So it's like what makes the Daleks and the Cybermen sound like they do. So I'll play a clip of
that. Withdraw now, Doctor, or the city dies in flames.
Who are you kidding? This ship is a wreck. You don't have the power to destroy London.
Watch as the humans destroy themselves.
Turn those lights off now. Turn London off, or I
swear I will use the TARDIS self-destruct.
Stalemate, Doctor. Leave us and return to Earth.
Oh, that's it. That's your great victory. You leave.
Extinction is not an option. Withdraw now.
Okay, so if you want to know how it ends, you're gonna have to watch Doctor Who yourself. But another famous usage of ring modulation is actually in the South Park ending theme, kind of like when the credits roll. I've actually never seen South Park, but I know it's really popular, so I decided to put it in here. Okay, so that last part that we just heard before I went to the next slide, that I think is like when the ring modulation is turned way up. But yeah, so ring modulation, as you can see from those two examples, it's not known for sounding very nice. Actually, when we were prepping this article and I was looking through like online forums, just with people who use ring modulators, someone called it the sound effect from hell. So it's not the prettiest sound, but if you tune it right and you use it in the right ways, it can actually sound really nice. So I found a nice clip of that. Okay, so now that we kind of have an idea of what ring modulation kind of sounds like, we can actually go into how it works. And so, ring modulation is actually a form of signal processing. And so, before we go into what ring modulation is, we should go into what signal processing is. So, what is signal processing? So, essentially, audio is like a sound wave, right? And so, in the music tech world, we call that a signal. And so, I like to think of this just to make it simpler. I like to think of these signals just as like sine waves or a wave like that. And then that sound wave is like traveling through time, and that's how we like hear it. So, because audio is a wave, the signal, we can perform all kinds of mathematical operations to process that signal, hence signal processing. So, I know we all paid attention in high school physics class, but for those who might need a refresher, or those who maybe didn't take physics, we are gonna just kind of go over some basics of like how signals, how audio works, in terms of like the actual wave. So the amplitude of a wave, which is like how tall it is, determines the volume of a sound. So like how loud it is or how soft it is. And then the frequency of a wave is how fast it's moving. So if you look at that vertical line that I put in the picture, it's sort of like how fast that wave is moving past that line. So the frequency of a wave determines the pitch. So like the higher the frequency, the like more high pitched something will sound, and then the lower the frequency, the more low pitched a sound will sound. So now we're going to go into actually like ring modulation itself. So it's actually a fairly simple form of signal processing. It's essentially multiplying two signals, so multiplying two sound waves together. So each of these signals has a special name. So the carrier signal is the original signal or the original sound. And it's the sound that we want to affect. So in the case of the Daleks, the first example, this is the signal of like the voice after talking without any distortion or anything on top of it. And then the modulator is the signal that alters the carrier. So this is usually a pretty simple wave, like a sine wave, so that when they're multiplied, the wave will still maintain like the quality of that original sound. Because if you have two like complex waves and you like multiply them, it just becomes all like indecipherable. But if you take like a complex wave like someone talking and a simple wave like a sine wave and you multiply them, it'll still like maintain that quality of the carrier or like the person talking. So yeah, you multiply those together, it creates a more complex waveform, and you have ring modulation. And so I think Laura is going to go into kind of more about what we actually hear. So maybe you should like introduce yourself.
I can do that. So for all the NU WIT people, my name's Laura. I'm from NU Sound, the president, and I'm just going to go ahead and keep going. So if anybody has questions, just let me know. So ring modulation is a kind of amplitude modulation. So as you can see from these pictures, I'll put in, like, this is an example so that people can sort of visualize it. We can see the wave on the top. We can call that frequency X. So it's a wave that's moving at a very, very like slow pace, right? Because frequency is like the number of up and down cycles that the wave's doing over time. If you have this first wave at like frequency X and your second wave going 12 times that frequency, so it's higher in pitch, when they're multiplied together, what you're gonna get is the same frequency as your second wave, but it's going to modulate the amplitude at the rate of the first wave. So in terms of like the multiplication of these waves, that's exactly this complex wave at the bottom. As you can see, that's exactly what it looks like. So it's just going to be changing how much the amplitude is going over time. So it's going from like low amplitude to high to low, etc. And then if we go to the next slide. So sonically though, what happens when you multiply two sinusoidal waves together? So this is the trigonometry part. I'm putting this in. This isn't like an NU Sound thing. This is more of like, because I trust that the NU WIT people are more sort of interested in the mathy part of it. But when you're multiplying two sine waves together, or a sine and a cosine, what you're gonna get is a wave. That complex wave is equivalent to two sine waves or cosine, two sinusoidal waves that are going to have frequencies like first frequency, so A plus B and A minus B, if that makes sense. So if you have sine waves of frequencies A and B multiplied together, you're going to have two waves that are frequencies A plus B and A minus B that are going to be actually sounding. So your result from the ring modulation looks like the picture from before, where you have like that amplitude modulating, but sonically, you can actually hear it as two different frequencies because of this trigonometric property. So that's why it sounds kind of, you get sort of more than one note out of ring modulation. It's because of this, because you're producing two sinusoidal waves out of your multiplication. You can go to the next slide. So these are what musicians who are not mathematicians called. They call them sidebands. So they're the sum and difference tones that are produced when you're multiplying the two waves. So if we say that our carrier has frequency X and our modulator has frequency 12X, then your sum frequency is going to be 13X and your difference frequency is going to be negative 11X, which is equivalent to 11X. So you're just going to hear these two frequencies out of your ring modulation. And that's the kind of like cool sound you hear. So we don't have to watch this video, or maybe we could, but this is just sort of goes into Star Wars sound effects and kind of explains it in other terms.
We can probably go into like the first minute or two.
Yeah, go for it.
One very recognizable sound from the Star Wars series was the radio or voice communication effect heard in battle scenes.
I copy, Gold Leader. Move into position.
Most notably in the final Death Star assault at the end of Star Wars A New Hope. These vocal sounds have a distinctive tonality that doesn't sound like standard radio interference. These effects were achieved using a ring modulator.
About 20 guns, some on the surface, some on the towers.
Ring modulation is a method of frequency mixing two signals, resulting in a complex combination of harmonics from the sum and difference of the two signals being mixed. A form of amplitude modulation, ring modulation was used in early science fiction television and film production to achieve strange and unnatural sound effects, including the classic voice of the Dalek from Doctor Who. Using a sine wave to modulate the human voice, this kind of ringing, distorted, but recognizable sound can be achieved. Let's try modulating a couple of signals through mutable instruments.
Okay, so the rest of the video just goes into how to make a ring modulator work, which is what we're going to do like right now. So I believe New Sound just had a like a Max MSP workshop, but no worries if you weren't there. We are going to kind of go over what Max MSP is. So Max, like the Max part of Max MSP, is a framework for developing interactive software. If you know what a GUI is, it's like a GUI, it's a graphical user interface. MSP, I think it stands for Max Signal Processing. So that deals with the signal processing side of Max. So that allows us to use Max with like audio signals. So if you're like a cool kid and you know what you're doing in Max, you would say that you would create a patch by connecting objects together with patch cords. So to kind of break it down, a patch in Max MSP is essentially a program. And then an object, this is a little confusing for computer science people, but an object in Max MSP is a function. Basically, it takes these inputs in its inlets and it gives these outputs in its outlets. Works just like a function. It's just called an object. And then the chords in your patch or your program determine the flow of information between objects. So like you'll have a chord from one outlet to another inlet of another object, sometimes to the same object. And that'll kind of determine where all your information is going. So again, if you wanted to follow along like on your computer with the patch making part of the workshop, then go to this link, download Max. You can also do it after the workshop. Tara will be sharing her screen when making the patch, so you'll still be able to see what's going on. And there we go. So this is sort of what a patch will look like in Max MSP. So you'll see, first thing, bottom left hand corner, you'll see this like lock or this unlock symbol. and that indicates what mode you're in. So Max MSP has these two modes. One is for editing and one's for listening. So if it's locked, that's for like listening and interacting with your patch. It's sort of like using it like from the user side. And then if it's unlocked, then that means you can edit the patch, and that means you can like drag things around, edit it, stuff like that. So if you're having some issues with like editing and testing your patch, check that button first. So next we have objects. And so you can make a new object with that button kind of circled at the top left corner. So the objects are all these like box looking things in Max MSP. And you can kind of see that they all have these inlets and these outlets. And then they're all connected together with patch cords. And so Max does this nice thing automatically where if your patch cord is like using audio or like a signal, then it'll make it dotted. It'll be a dotted line and it'll be yellow. So that just kind of helps you figure out like what's going on. And then like normal, regular like values are sent through those like gray patch cords. So this looks kind of like a tree if for those who are in computer science and work with trees a lot. So in terms of like the flow of information, Max starts at like the top of the program and works its way down. And then if two things are at like the same level, then it goes right to left. So that's sort of like the order of operations for everything in Max.
Oh yeah, so the way Max is built from the sort of MSP perspective, like if you see the sort of phone switchboards, like that is really what the graphical UI is really kind of trying to emulate. And I put this picture of Wendy Carlos there on the right. So she's the composer. She wrote all the music to The Shining, Clockwork Orange, Tron, and what she has there is like a modular synthesizer. So basically it's this electronic musical instrument that basically processes signal by basically patching things in. So you're passing that audio signal through an instrument and processing it as it goes along. So that's really what Max is like meant to look like, just if people didn't know.
Cool. So I think Tara, this is your moment to shine.
My moment. Oh wow.
Before we go on, are there any questions? Anything that needs clarification?
Okay, so now we're going to get into making a simple ring modulator ourselves. So I'm going to share my screen, and that picture that's in the PowerPoint is actually what we're going to make, and I will share the patch at the end for everyone to get. And if you want to follow along in Max, feel free. And I'm going to share my sound. Okay. Can everyone see my screen?
Yes, but I was going to ask really quickly if anybody still needs the download link at all. Maybe someone can throw it in the chat just in case if people
It's
need
already
to
in the chat.
get a free trial still. Oh, is it?
Yeah.
Thank you.
Beautiful. Okay, then if there are no further questions, I'm gonna get started. So for a simple ring modulator, we discussed earlier that you need a carrier signal and you need a modulator signal. So I wrote these down over here in comments so we can tell what's what. We're gonna make a really simple ring modulator. So we're just gonna be multiplying two simple sine waves. So the way to get a sine wave in Max is that you need to click on the top left over here. It says object. So we're just gonna click there and you should get a box that looks like so. And in it, we're gonna type cycle. And you can see the second one has like this squiggly line. It's called a tilde. It just means the object is gonna be dealing with signals. That's what the squiggly line means. So we're just gonna click on that one. And so here's our sine oscillator. And you can see that there's inputs on the top and outputs on the bottom. So an input would be a frequency, which would be the pitch. So to give it an input, we're going to take a number. So numbers are a box like in the middle with a triangle. And I'm going to give it the middle one, which is a floating point, so we can be exact. And the way you connect them is that you just bring the output of the floating point to the input of our sine oscillator. And so now that we can specify a frequency that the sine will oscillate at. Any questions so far? So this is basically all we need to get a sine oscillator. So the great thing is that since we're making a really simple one, all we can do is just select it. You just want to click and drag so you got both of them selected, and we can just copy and paste it for our modulator so that we have another sine oscillator. So to make a ring modulator, as we said earlier, you want to multiply the signals. So we're going to need a new object. And in it, since we're multiplying signals, it's exactly as it sounds like. We're just going to need the multiplication sign. And the second one is for signals. You're going to need a tilde. And I like to give it an argument too. As you can see here, it'll say multiplier. If you just give it one input, it'll just multiply by whatever you put in here. But I just like to put in a 1, which is the identity. So even though we're multiplying two signals, just will be the same output. So connect them both to the top. See, the left is is input 1 and the top right is input 2. And the result will be the result output here will be our ring modulated signal. So we want to be able to hear this. So we're going to need an easy DAC. An easy DAC is basically just an on and off switch. So we get a new object and you just type in there easy DAC, easy DAC. And you should get this box with like a volume looking control on there. But so we don't hurt our ears, we're also going to put a volume control. So another object, and it's called a gain. It's just looking like a simple slider so that we can control what at level our output signal will be like. So the gain's a little hard to see, so I'm going to make it a little wider, but it has two outputs. We want the left one, which is the signal that goes through it. The right would be the slider value. We don't need to do anything with that, so we're just going to connect both of the inputs for the easy DAC from the left output, the signal output from the gain. And so we just got to put our signal in there into the top left one, and this is it. So how do we know if it's working? We love visuals, so the way that we can see the signals is that if we get a new object, it's called a scope to see the signal. Okay, so we got a scope to see our signals. So out of each of our sine oscillators, we can put a scope. And we can put one at the resulting out of our gain to see what the resulting wave looks like.
Tara, what's a gain again? Is it the volume?
Yeah, it's the
thing?
volume control. So it just looks like a simple slider. I can click on it like this and it'll just control at what level we hear it, so we don't like blow our eardrums out.
Does the speaker output, are those both inputs for the left and right channels, or are they just two separate?
Left and right channels because it's stereo. So we're just gonna put the one signal into both of them so that we can hear it in stereo. All right, so and needed one more scope for our resulting signal. And we can get another object, which is called a spectroscope, so that we can see the actual amplitude and see the wave shape of the resulting signal. Connect that also from the output of the gain. And this is it. So now let's test it out. The way.
Wait, sorry. Sorry, Tara. What's the name of the object for pitch again?
For what?
Pitch, like your frequency.
Number
That guy.
box.
Is that a number?
Yeah, it's just we're just having a number box here.
So at the top, there should be the one with the triangle, like at the top where you make a new object. There's one that has a triangle in it, and the one that has a triangle in it is for numbers. You can choose an integer or a floating point. It doesn't really matter. for the purpose of
this
this.
drop-down menu over here. The first one is an integer, the second one's a floating point. It doesn't matter, but I use the floating point. So that's how we're going to specify the frequency.
So the top one is just a number, and then cycle is the block that transforms it into a wave of frequency of that integer.
Yes, that is correct.
Okay, cool.
Okay, so anyone have any other questions? If not, then we can test it out. So right now we were in editing mode with an unlocked screen. So we have to lock our screen so that I can't move these things around when I'm clicking stuff. So to lock the screen, bottom left corner, right now it looks unlocked. If I click it, it looks like it's locked. So, and if I try clicking on stuff, I can't move anything now. And that's how you know you're in the right mode. So first thing we're going to need to do is that for a carrier signal, we need to give it a frequency or a pitch. So does anyone want to volunteer a number? And someone read it out for me because I can't see the chat.
So just for reference, our hearing range is between like 20 and like, what is it, like 20,000 hertz?
Yeah, 20 to
It's just for
20,000.
reference. So that's the unit of measurement, which is hertz. Go for it, Coop.
What about 808?
808, solid number. All right, and I'm just gonna set our modulator at first to 1 and see that what that here is like, what sounds like. And this is our on and off switch, the easy deck. So now I have to click it. And can we hear that? Nice. So right now it kind of sounds like a pulse because as was discussed earlier, what you're hearing are the sidebands. So that's just the carrier plus the modulator. So 808 plus 1 is 809, and 808 minus 1, which is 807. And since they're so close, we hear this pulsing kind of thing. So if we raise it, this is what it'll sound like.
Oh wait, you should turn down your volume a bit if you're gonna be talking because it's starting to mess with your voice. I don't know if that changed anything.
One second.
Also, check if your speaker switch is local, because I can hear something else.
Yeah, I can hear
It
something
could be
else.
another patch that's going off in the
Yeah,
back.
it's the bonus one. I realized that now. All right.
There we go.
Okay. Can we hear this? Okay, so this is the pulsing from originally. And if we raise it to something like 100, we won't hear a pulse anymore, but you can hear some modulated sine wave. So as I move the modulator up, if you're watching the spectroscope over here, you can see that we can now see two peaks since 800 plus 200 is a greater sideband now. We have a larger distance between the two peaks. So this is about it for our simple ring modulator. Does anyone have any questions?
Someone asked where we get the lines. I think they're talking about the scope and and the spectroscope things, but
so this box is called a scope, SCOPE, with a squiggly line for signals, and this box is a spectroscope. These three are all the same thing. So right now our waves aren't looking too great because the default window is a little too zoomed in. So you can always change the size. If we unlock our window, bottom left corner, and we click on it, so it's highlighted, there's an eye on the right over here, which says inspector. And we can see our buffer size is 128. So I'm going to change that to 32. And samples per pixel, let's change that to 4. So now we can see our wave. It's moving pretty quickly because 268 hertz is pretty fast. But now you have a pretty visible wave. Any other questions?
Just a quick question. It's like, where do we get those lines from those sine waves to the output?
To get like a visual on the scope.
How do we do the chords again?
The chords? Okay, so you just left click on one of these. You'll see it highlighted. See, like when I'm hovering over this, the yellow one is like highlighted and it's a little bigger. If I just left click, you get a chord, and you gotta hover close to where you want it to connect. And when you see highlighted like this orange one, you just left click again. That's how you connect patch chords. Any other questions?
What's the graph in the bottom right showing us? What's
It's
that?
showing you, instead of it looking like a sine wave like this, you can see like the amplitudes, like how loud it is, instead of just seeing, because all sine waves like look the same. So now you can see the different amplitudes and at different frequencies.
Okay.
So the right one is the sideband that's plus the modulator, and the left one is the sideband where it's carrier minus modulator.
And which one was that called? Is that the spectroscope?
Spectroscope. Yeah, so the difference is the spectroscope, you have frequency on your x-axis. So what you're seeing is all of the different frequencies. And then like the y-axis is amplitude. So you can see frequency sideband 1 and sideband 2. And then in your scope view, you're seeing time as the x-axis and amplitude as the y-axis. So you're seeing it in the time domain versus the frequency domain. So in your scope graph, you're seeing like the wave that I showed you in the first example. And then in the second one, you're seeing like the actual frequencies of that combined sort of complex wave, if that makes sense.
Yeah, I kind of think of the spectroscope as like what pitches do we have in this sound. So you see that there's like two distinct pitches in this sound, and they're at where those like bumps are.
So if there are no other questions, we have a little surprise. This is only the base of what ring modulation can be used for, as seen with knowing that ring modulation is used to make the voices of dialects and Think Cybervintu and the South Park theme. So I'm just going to bring up. Okay, here's a patch that I made. It's color coded so we can see. Trying to figure out how to zoom in.
You might be able to use the scrolling bars up like the side and the bottom to get it.
Oh, perfect. That's what I wanted. All right, thank you. So right here, this is, it looks pretty complicated, but the only difference is that I have multiple options for our carrier signal. And oops, this is why you lock your screen. And the purple over here is the simple modulator that we have. It's the same thing for the modulator, and I just added more inputs for our carrier signal. So first thing that we can listen to is, oh, remember to lock your screen, bottom left. So we have a menu over here. Sadly, the menu is showing up on my other screen. I don't know how to fix that.
I like the background, Tara.
Thank you. If I don't have my screen maxed, okay, now we can see the menu. It was showing up on my other screen for some reason, so I guess I'll just demo it like this. Can I make it slightly bigger? There we go. Okay, so now on our menu, we have options for sine, which is just the simple one that we just did. Can test to see if that one works as well. So it's doing the same thing. You can see I altered the windows so that we can see the waves a little better. Can change the modulator, and we see that it still works all the same. So our first is an audio sample, just like me saying testing 1, 2, 3, but now you can hear what happens if you put it on voice.
1, 2, 3, 3, 2, 1. hello, hello. Hello, hello. Testing. 1, 2, 3. 3, 2, 1. Hello, hello.
And so since we're altering it, you can make it sound really trippy and alter the modulator like while something is playing.
3, 2, 1. Hello, hello. Hello, hello. Testing. 1, 2, 3.
And then so we can see also what happens on a sound. So next we have a sample of just a simple guitar track. I have a toggle over here which can turn off the ring modulation so that we can just hear what it sounds like without ring modulation.
The sample isn't playing, Tara, I think.
Oh, okay, that's fine. I'll just play on all of them so I don't forget. Got a nice slow jam on the guitar. Sounds pretty nice. And then with ring modulation, it's gonna sound completely different. And now we get into something a little more sci-fi sounding. We have a sample here of a rusty swing. So it's just, sound that everyone loves, a great squeak. And with ring modulation, I'm gonna start it off as like 100. You can tell like it doesn't actually sound too bad then, like nothing too drastically changed. But then if I change it to a really high frequency, as someone described earlier when I demoed it elsewhere, it kind of sounds like aliens kind of communicating. And as our goal in the beginning of the presentation, you can even make yourself sound like an alien. So the last input for our carrier is a live audio input. So you can hear me speaking live, and I'm just gonna mute myself on Zoom so that we don't get an echo. Hello, can everyone hear me? This is me without ring modulation. Okay, so now if we turn it on, well, first I'm going to turn the ring modulation back down. We turn it on.
This is what I sound like now. Hello, hello. New sound and new wit. This is me as an alien. I can make it higher, and I'll get a higher frequency voice mixed with a lower frequency. Hello, hello. And this concludes the end of the workshop. Thanks for everyone for coming. I'm gonna throw it back to Emma unless anyone else has any other questions.
Question, Tara, are you going to answer questions in the voice?
I can if you want me to.
Yeah. Coop, do you have a question for Tara?
I wasn't sure if I should save my question. Should I ask my question?
This is the end. The only thing left
This
is
is
our
the end?
QR codes. So
Okay, I have a question for both Tara and Emma.
I will post the patches in the chat too.
Awesome. I have a question for both Tara and Emma. How are your days? How was your day today?
it was all right. I went to work. Don't tell my employer this, but I avoided work as well. And yeah, I forgot to get
You're
carrots
still
for my dinner.
recording. You're still recording.
Oh, it's fine.
Tell me out about the day
No.
reserved for people who show up on time.
We can edit it out. I went to the grocery store because I forgot carrots for my dinner, and then, like an idiot, I went out with like socks and Birkenstocks on in the snow, and I fell multiple times. So that was my day.
Robotera, how was your day?
So did you want me to answer like normally or? Okay, well, my day was, I don't like your echo. Hello, hello. Okay, my day was pretty hectic. I did not sleep yesterday, so and was supposed to sleep last night, but I had lots of homework to do, so I was gonna pull another R-nighter, but I literally passed out because that's just how tired I was. So fun times. And I actually finished my homework somehow right before this meeting, so I'm pretty chill now.
I'm having brownies for dinner, so that's my day. Yeah.
The one thing I love about being an adult is I can eat like brownies and cookies and ice cream whenever I want.
Is that
That's
a true sign of adulthood? Is like
eating cereal for dinner. It's eating cereal for dinner.
Right. True adulthood is making the executive decision over your own life and choosing breakfast for dinner or cake or
No, breakfast for any meal is valid.
breakfast all day long, all the time. Anyway, Emma, take it away.
I don't got much. These are our clubs. We have emails and QR codes. Unfortunately, we meet on the same days at the same time, so you kind of have to choose which club to go to. But yeah, if you're interested in us or any of our social media stuff, here we are.
Yeah, and we
basically what we're saying is on any given Tuesday night you have options.
Yeah, you have options.
You got options.
And if you miss an NU Sound meeting to go to an NU WIT meeting, we won't be mad at you.
No.
That's
But there's recordings for both, so you know.
There's recordings for both. Yeah.
We'll both love you equally, whomever you choose. But
yeah, but thanks, Emma, and thanks, Tara, and stuff. Oh, what's the NU Sound website? Is it not on the QR code? I might have effed that up, but I'll throw it in here just in case.
We can send out everything, at least to the new members in our like post-meeting newsletter.
Yeah. I'll check. I think I should have put the link tree as the QR code. And if I didn't,
do we want to stop the recording?
Yeah, go ahead.
Yeah, I can do that.
I can edit all the and